Thank you very much, and thank you for the invitation to speak. I was born in Australia, but I now live in the United States. But this is my first time to Korea, to Asia. I was Australia, America, not in between. So it's wonderful to be here. It's just lovely. So thank you. I am giving 2 talks, and tomorrow's talk will be different to today's talk. So if you don't follow, it's okay. Yeah. So I'm going to tell you about quadrisecants today. I'm going to give a very brief sketch of some proof. Essential secants are a technical result which we'll need in the proof, which I may skip if there's not much time. And then I want to talk about more recent work and some open questions. Quadrisecant secants in general, we can consider lines which intersect a knot, and we want to orient our line. And an n-secant line is an oriented line which intersects the knot or closed curve in at least n places. And a secant will be a 2-secant, a trisecant will be 1, 2, 3, try 3, and a quadrisecant will intersect in 4 places. So we can do a dimension count. So if the knot is generic, meaning reasonably nice, and we think about 2 points on our knot, there's a 2-dimensional family of secants. It's 2-dimensional. If we add in another point, so we've got this 2-dimensional family of secants. If we add in another point, it's a 1-dimensional family. And if we're a quadrisecant, that's a 0-dimensional family. So we expect finitely many quadrisecants. That's sort of a rough dimension count. And higher order secants, 5 secants, 6 secants, we don't expect them to appear. But the unknot has no quadrisecants, right? No quadrisecants. So something interesting is happening. And I wanted to talk about different types of quadrisecants today. This quadrisecant here looks different to this quadrisecant here. So I want to tell you about the different types. So I'm going to compare the order along the line, so that's A, B, C, D. And I want to compare the order along the knot. And in this one they match, and I'm calling that simple. And in this one, these two are flipped. So I call this flipped. And then in the end, this one here, I'm going A to C to B to D versus A. So I'm sort of like, I'm bouncing backwards and forwards. So I say this is an alternating quadrisecant. And I don't really care about the order along the knot. I could have drawn these differently. These are just representatives of the 3 types. So a theorem I proved a long time ago is that there's at least one alternating quadrisecant. So this sort of should make you happy because there's some winding around here. It's not like the unknot. So if you're knotted, something interesting is going on, you expect to see something like this. So this is a theorem I proved quite a long time ago. If you're non-trivial, tame knot, you have at least one alternating quadrisecant. So quadrisecants have a very old history. They come right back to the 1930s in Germany when topology was just starting. And Erika Panvitz, she showed that every non-trivial generic polygonal knot has at least 2u² quadrisecants where u is the unknotting number. It's an interesting result. There's no discussion of type, Just she proved they existed. And in fact, this, if you read the book by Reidemeister, the first knot book, he talks about her result. It's kind of cute, sort of. And then Morton and Mond in 1980, just independently, didn't know about Erika Punvitz's work, showed that there's at least one quadrisecant if you're a polygonal generic smooth knot. It's just an independent result. And then Kuperberg in 1994, Greg Kuperberg, proved that every non-trivial tame knot, not just polygonal, not just a special kind of polygonal, but any kind of tame knot has at least one quadrisecant. So the idea is this would be a sequence of generic polygonal knots, and then I take a limit to my tame knot. I approximate this by these polygonal knots, and we think about our quadrisecants limiting to something. And the question is, what happens to points in the limit? Do points come together or do they stay apart? So Greg Kuperberg introduced another topological idea to fix this problem of points coming together in the limit, and I'll talk about that later. And then I strengthened, I don't know why this goes this funny way, I strengthened this result to having this extra property, which I'll talk about, called essential in the limit. A non-trivial FTC knot is a knot of finite total curvature. So that means literally if you add up the tangent vectors, the total sum is finite. Finite total curvature curves have left and right tangent vectors everywhere. So they're made up of smooth pieces and corners, and they can have cusps. But they're a general kind of knot. At the same time that I was proving this, there's a very interesting result by Ryan Budney and Jim and Dev and about alternating quadrisecants. They were looking at long knots R and R3. So these are knots where the ends go off to infinity, and then you have the knot in the middle. And they proved that, they proved that you associate a plus or minus 1 to each quadrisecant, you add them up, and it corresponds to the second order Vassiliev invariant. And I wasn't sure of what people knew, so if you don't know what this is, it's the coefficient of z squared in the Conway polynomials, a way to think about this invariant. So this is very interesting. So this gives a different count on the number of alternating quadrisecants, but some non-trivial knots have 0 V2. So both results are sort of needed somehow. And this question of counting quadrisecants, I'll just keep talking about it throughout today's talk. So I thought I might introduce sort of what I'm going to talk about tomorrow, that I'm interested in geometric knot theory. I'm interested in using topological results to say something about the shape of knots. And this is a very famous theorem, the Ferry-Milna theorem. The total curvature of a non-trivial tame knot is at least 4 pi. And maybe you know about total curvature if your curve is at least twice differentiable. You're just adding up the tangent vectors. But Milner proved an equivalent definition in his paper. So if you've got a polygon, what you do is you just add up the sum of the exterior angles. And then if you're any closed curve, you take all polygons inscribed in that curve. So you take right, all polygons inscribed in this curve, finer and finer polygons, take the supremum, and Milna proved these two things are equivalent in his paper. So that's the total curvature. Interestingly enough, like in the history of quadrisecants, so Erika Panwitz was in Germany, and Heinz Hopf and Reidemeister knew about her work, and I believe that Heinz Hopf knew about total curvature, knew about quadrisecants, and may have suggested this as a project to her. I mean, Schmidt was her advisor. The history is vague, but there's an interesting connection here historically. And so why is this true? Why does the existence of alternating quadrisecants imply this result? Here is an alternating quadrisecant. It's a very inscribed polygon. So if I think about starting here, I walk from A to C, and then I turn around pi and walk from C to B. And then I turn around pi and I walk from B to D. Then I turn around pi and I come all the way back to A. I turn around pi and I'm back, right? So that's 4 pi. It's very, very cute. Another result, in fact, why Greg Kuperberg was interested in quadrisecants, I think I was talking with him, and John Sullivan was my PhD advisor when we were talking about this. So every non-trivial tame knot has non-empty second hull. So you know the convex hull, it's just a familiar object. The second hull is you take a point in space, you think about a plane through that point, and you ask yourself, how many times does the knot intersect that plane through that point? And we want it to cut 4 times. And not just this plane, but any plane through that point. We want the knot to cut at least 4 times. Does that make sense? So there's a collection of points. So anything in this mid-segment will be in the second hull. So you just have to think about that. But any point here will be in the second hull. So
it's the Milna theorem.
Yep.
It's strictly inequality.
Is at least, yes. So it's strictly 4 pi. Yes. Yeah. Good. Okay. So what I want to do is give a little sketch of why we might expect quadrisecants and indicate some of the technical parts. And then I can rush through that if we need me to. But then I'll talk about other quadrisecant results that have come up since this time. And on Wednesday, I will talk more about these geometric results, how you use topology to say something about the geometry of knots. So, talk about trisecants. So these are lines which intersect a knot in 3 places. Each point of your knotted curve. So knotted curve, for me, means non-trivial tame knot. I didn't want to write non-trivial tame knot all the time, so I abbreviated that to knotted curve. So suppose this is false. Let's pick a point which is not the start point. If this is false, there is a point which is not the start point of a trisecant. So a lot of there exists and for alls and negations there. But I'm going to construct a disk with that point. I'm constructing a disk made out of these line segments. And I've assumed this point is not the first point of a trisecant. So this picture is good. I'm never going to have the boundary intersecting these lines because it's not the first point of a trisecant. So this is an embedded disk with the knot as its boundary. And this means that the knot is the unknot. It's an equivalent definition. And that's a contradiction because we assumed it was knotted. And I spent some time on this easy proof because the proof that there are quadrisecants are like this, is like this. We make an assumption, we do a lot of technical stuff, we construct the disk, a knot with an embedded disk as its boundary, and that's a contradiction. So the proof of quadrisecants is like this, just longer and harder. And then this is just a cute result. There are points which are not the second point of a trisecant. So you just pick a point that's on the widest part of the convex hull of the knot. There's no way for this to be the second point of a trisecant because there would be a point that was further out. So it's just very straight. It's just cute. We might need this. Okay, so I'm talking about trisecants because eventually I want to understand alternating quadrisecants. So it turns out that there are two types of trisecants as well. So here I'm comparing oriented line and oriented knot. So I'm thinking about the cyclic orderings. And there are two types, same and different. So here the order along is A, B, C. But the order along the knot is A, C, B. So that is different. So this is a trisecant of different ordering. And this one down here, the ordering along the line is A, B, C. The ordering along the curve is A, B, C. So they match. So this is a same trisecant. And why am I doing this? Because I want to understand alternating quadrisecants in terms of these trisecants. So the idea is that here is my alternating quadrisecant. If I look at, I can think about this quadrisecant as four intersecting trisecants. I have ABC, ACD, ABD, BCD, right? I have four trisecants overlapping. So I just want to consider two of them, the two that have the first two in common. And what you can do is you can convince yourself that, well, A, B, C here, A to C to B, so that's a trisecant of different ordering. But if I think about A, B, and then D, I go A, just ignore that, and then I hit B, and then I hit D. So that's a trisecant of same ordering. So we're capturing alternating quadrisecants by looking at intersections of these sets. So now we can do some math. So what we're going to do is we're going to think about trisecants, which I'm calling script T, in triples of points on the knot. So I can think about the knot, cross the knot, cross the knot, and look at the set of trisecants there. And then I can think about the set of secants and the subset, which is the set of trisecants. So let me do this. So here I have the knot, cross the knot, cross the knot. I'm thinking about this side and this side as being identified. And when I'm thinking about this, each of these points on this curve is meant to be a trisecant. Okay, so when I pick 3 points on my knot, right, these 3 points will be in this space somewhere, but they're not necessarily a, okay, this is not meant to be here. That's not intersecting, right? These 3 are meant to be a trisecant. So, a lot of technical detail I'm going to suppress, but if you make the right assumption on your knot, you can prove that the set of trisecants is incredibly nice. Compact one manifold with boundary. And the boundary of the set of trisecants occurs when 2 points come together. Okay? So that the boundary will be on the big diagonal where 2 or more points come together. So there's a lot of details here that I'm just not going to talk about. And then you can project down to the first 2 coordinates. Remember, we're interested in the first 2 points. So I'm going to project pi 1, 2, sorry. So back here, I'm going to take the projection of this thing down to the set of secants. So what does this picture mean? This is k cross k, and then this line here is the diagonal y equals x. So I just want to unwrap this. So these sides are identified, this is identified. So I just want to redraw it. Okay, so I just the same picture, just drawn in a nice way. So again, very careful assumptions here will mean that you never see, so this is a very nice one manifold, and when you project you don't want to see these kinds of bad sort of intersections. You're going to only see nice intersections. So you're not going to see this, you're not going to see the boundary ending on a curve, you're not going to see this. You'll see very nice things under this assumption. So just pretend everything is nice, and it is nice, but it's too technical to talk about. Are we under control? So really downstairs here, if I have trisecants of same order, trisecants of different order, this point here will be an alternating quadrisecant. Okay, so this is nice. We've changed the question from this idea of a line intersecting a knot, and we've looked almost at 2 submanifolds in a manifold. Do they intersect? So that's a nice transition, change of question. This is something we can get our hands on. Okay, so we're nearly there. We're nearly there. Again, this is just a sketch. So within this set, trisecants sit in here in a particular way. So I'm going to call this the bottom boundary and this the plus boundary just to distinguish. And I want to think about what happens when you walk up. So it's like I'm starting at a point and I'm walking along as I walk up this line. Okay? And then I want to ask myself, how close do the family of trisecants come to this boundary? And how close do the family of trisecants come to this boundary? And it will depend on the type of trisecant. So here I've got x, y, z, and I'm going x, z, y. So this is different trisecant. And remember, I'm a generic polygonal curve. So in the set of secants, I'm looking at the points x and y. So how close can these points be to x equals y? Well, I have to go at least this edge length, and maybe a bit more before I can reach y. In fact, I have to have generic requires that no 4 vertices are coplanar. Okay? That's part of the definition of generic. And so I will never see x, y, z and then another line. I will always need an extra edge length. So that means when I'm walking up from this boundary, I have to miss 2 edges, and the first place that the trisecants of different order could be would be here. Okay? So the idea is that trisecants of different order stay away from this boundary. And the same argument can be used to show trisecants of same order stay away from this boundary. So I might have trisecants of same order, that's okay, but trisecants of different order just don't get there. They'll turn around and do something else. Okay? Okay. So let's think about this. Let's do some graduate level homology. Let's do some Maya-Vietoris arguments. So we have an topological annulus, and we have 2 sets, trisecants of same order, trisecants of different order, and they stay away from these different boundaries. So you can do a very straightforward argument and show there has to be a curve. If these 2 sets do not intersect, there has to be a curve winding once around. This is in, oops, right? Winding once around. There has to be a curve if they do not intersect. A very, very useful idea. Okay, nearly there. So that's what I just talked about. So what we're going to do is we're going to use this path to construct a disk with a knot as its boundary. So I think about this point on this curve. So this is going to be a point AB, say. So here is A, here is B. What I'm going to do is I'm going to look at the direction from A to B, but then take the ray in that direction from B off to infinity. I'm going to go outside. And I'm going to do this all the way along this path. So I'm going to get a bunch of rays, right, walking around. So let's skip some more technical details. After some surgery, after some surgery, and some pretty heavy metal theorems from 3-manifold theory, okay, big sledgehammers here. You can get an embedded disk with a knot as its boundary. So I'm lying, right? I haven't told you any of the details, but it's doable. So this is a contradiction to the knottedness. So we assumed no alternating quadrisecants. Let's just recap. These sets don't intersect. We can find a path, construct a disk, show you must be the unknot. So that means if you're the knot, these sets must intersect. So you must have a quadrisecant. Okay, with some lies.
Excuse me, can
yes.
you tell me in more detail way of the second line, how to construct the disk?
Yes. So each point on this path, that's 2 points, and they're on my knot. So I look at the vector from A to B, and then I go from B to infinity in the direction of that vector. And then, I don't know, there'll be some other points and I'll glue in another vector. I'll go, oh, you need to adjoin the point at infinity.
Yeah.
Oops. Need to adjoin the point at infinity.
B would be the boundary point.
Yes, yes. So yeah, this is the knot here, and the disk is out here.
So you didn't assume that TS and TD are not empty, but because the intersection is not empty, they're both not empty.
Say that again.
So you didn't assume that TS and TD are not empty, but
They have to be not empty, because every point is the first point of on the knot is the first point of a trisecant.
But that says one of them is not empty.
So if you so each point of the knot is the first point of a trisecant. That means I have a trisecant that's either TS or TD. So so if I look at ABC, this is a trisecant. Let's suppose ABC exists. Well, if I consider, so AB is in TS. Well, CB is in TD if I walk along this way. So every physical, if I just think about this tuple and don't care about the order, there's one guy you see twice. You see twice. Does that make sense? Yeah. Okay. So before I talk about this topological idea, I'll just say that in work I've done more recently than this, you can show that using considering this diagram more carefully, and I will talk to you about this in detail, but you can show that there are a certain number of paths from this side to this side. You can show that there are twice the unknotting number of paths from this side to this side. And that involves looking at disks and counting the number of boundary singularities. If you have a strand passage, if you think to become the unknot, if you think about the disk, then there'll be for each, if it's unknotting number 1, you'll have 2 boundary singularities. So you can use these kinds of arguments to count the number of curves which go across. It's so because I'm glad you asked your question, because this guy appears this way and this way, appears twice in this picture. When I count the number of curves going across, I'll have 2 times the unknotting number of intersections between TS and TD, but they each appear twice. Each quadrisecant appears twice depending on your order, which is why I think there's the unknotting number of alternating quadrisecants. So anyway, that's later. So yeah, I've talked about this limit argument earlier, right? You prove things for generic polygonal, and you approximate, and you hope that points don't come together. So we have time. I will go through this quickly. This is another topological idea, and what we want to do is we want to think about a theta graph. A topological theta graph. So I just want to think about curves joining 2 points A and B, and this is a general idea, but the special example is the picture, right? Arc alpha is the knot from A to B. arc eta is the arc of the knot from B around to A. And then this arc beta is the secant line from A to B. So it's a general idea, but we can use it in this specific case. And then, so I want to think about the complement of the knot, i.e. the complement of alpha union eta. And I want to take this curve delta, and I want this to be parallel to alpha union beta. So parallel means this is a nice embedded annulus, because it's a bit hard to talk about parallel when you have corners, but we can understand what this means. And I want this parallel curve delta to have zero linking number. To have zero linking number. That means it's trivial in the homology of the complement of the knot. Then you ask, is this curve delta trivial in the fundamental group or not of the complement of the knot? Okay, so that's an interesting idea. If it's trivial, we call this thing inessential. If it's not trivial, we say it's essential. So I drew this picture a long time ago before things changed. Here is a secant line here, and if we draw our parallel delta, if we draw our parallel line delta, this curve delta is trivial in the homology and the homotopy of the fundament of the complement of the knot. So this is nice, inessential. This guy here, as you can see, there's always this puncturing. So it's non-trivial in the fundamental group. So this is a topological idea which will also give geometry, and tomorrow's talk I'll explain how the idea of essential can tell you something about the distortion of a knot. It's an interesting problem. So some things about, another way you can think about this definition if fundamental group and homology is a little too much before lunch. You can think about inessential means, this was Kuperberg's original definition. You're inessential if you can find a disk bounded by the secant and this arc, which has no other intersections with the boundary of the knot. And you're essential, like this curve. This yellow curve, this guy will be essential because no matter which disk I fill in, there will always be a boundary intersection with the rest of the knot. It's a different way to think about the same idea. Choose which one you like. Okay, so when this comes to quadrisecants, so if you're unknotted, this is again basic sort of knot theory, topological knot theory, you're always inessential on any side of your secant. And the converse is true. If you know both arcs are inessential, then you also know you're the unknot, and that's just a Dane's lemma argument. So I want to talk about a secant being essential if both arcs are essential. So here, this arc is inessential, but because this is a knot, the other arc has to be essential. So when I'm talking about essential secants, I'm interested in these guys. So I have to be essential on both sides. So, and then when I want to talk about quadrisecants, the only place that in the limit, so we're doing these limiting arguments, can points come together? When you look at points A, B, C, D, the only place you have to worry is this points B and C coming together. because A and B can't come together without A, C, and B all coming together, right? And they're not going to do that in the limit. So I just need this segment here to be essential. And if I want to have essential flipped, I'd want to have CD and AB be essential. And if I wanted to have simple, I'd want this guy AB, BC, and CD be essential as well. So anyway, the idea is that with the proof, you do everything I just said, but put in the word essential. And then you won't have the problem of the points in the limit coming together. I hope that's intuitively obvious. If it's not, I can tell you more later. Okay, so I thought in the last 10-15 minutes before lunch, I would tell you about other results about quadrisecants. And something you may have wondered is, my title was Quadrisecants of Knots and Links. What about links? So Panwitz, Morton, and Mon both prove that if you have a generic non-split link with two components, then you have a quadrisecant intersecting in the order AB, AB. So that's interesting. And then Greg Kuperberg proved that every non-trivial link has an essential quadrisecant. And he didn't really talk about different components so much. You might have this or you might not. For example, if one of your components of your link is a knot, you'll automatically have your essential quadrisecant. So his was a more general result, but the point is it's gone from generic to every, and that's the interesting story. Greg Kuperberg was interested in this problem because of this corollary about algebraic surfaces and degrees, and this is not my area of expertise, so I'm reluctant to say anything more about that. But this is how he came to quadrisecants, and he was interested in this question. Okay, Julia Vero, not Oleg, but Julia Vero, looked at lines and looked at curves, links in real projective space. Actually, I will say that Greg I talked to Greg, and he said that if you have a RP3 and you have a flat, no, I won't, I'll do this later. Won't say anything, sorry. I'll come back to that. Julia looked at closed curves, and she's assigning a weight plus or minus 1 to these lines, and she's relating it to the linking number of those curves. And she has results. She has a whole bunch of these results. I only wrote down one. And some of them are to do with knots, and some of them are with links. And this idea of assigning a weight and relating it to the linking number is a common theme when people look at quadrisecants and how you count them. So back to just quadrisecants, Fiedler and Turkin, they have a paper titled Fiber Quadrisecants of Knots. I don't know if it's published or not. So they have a very interesting idea. They take a line in space, and then they take half planes attached to that line in space, hence this word fiber. So they're fibering R3 by a line and these half planes, and they consider knots transverse to these half planes, and they look at knots and they move them from one knot in a knot type to another, and they look at how they look at how that isotopy affects the number of quadrisecants. They again use a weighted sum idea. Their weighted sum is different. They map from this space to a thickened torus, and their weighted sum is a winding number of curves crossing each other. It's a different kind of idea. It's an interesting paper. This is a very interesting thesis by Garrett Flowers. He's finished now. He was a student of Ryan Budney. So Ryan Budney, this BCSS result was the one about the finite type invariance and quadrisecants. So that result was about long knots in R3. So Garrett joined the point at infinity and thought about S1 and S3. So Ryan Budney and Fred Cohen have a very nice paper where they talk about the homotopy type of R in R3, S1 in S3 versus S1 in R3. It's a very nice paper if you're ever interested in that question. Oh, wait a sec. We have a long knot. Okay. This is meant to be a long knot. It's not, but we'll just pretend it's a long knot. Now what we want to do is we want to adjoin. This is meant to be the point at infinity. Okay? So we can think about quadrisecants of these long knots. We can join the point at infinity. So this line is going off to infinity, so there'll be another intersection point here. So the natural class of objects to think about is not 4 points on a line intersecting the knot, but five points on a circle intersecting the knot, and intersecting the knot in a certain order. Intersecting the knot in this kind of order. So if we do a dimension count, we have 5 points in S3. So that's 15 dimensions. 3 plus 3 plus 3 plus, yeah, it's 15 dimensions. So that's a big space. 5 points on S1 is 5 dimensions. 5 points on my circle, well, 3 points, so that's 9 dimensions will give you a circle, right? You pick 3 points arbitrary to get a circle. You want the other 2 points to lie on that condition. That's an extra 2 dimensions. So that's 11 dimensions. So we have a 15-dimensional space, 5 points on the knot, 5-dimensional. 5 points on a circle is 11-dimensional. That's 1 dimension's worth of intersection. Okay? So what I'll show you a movie in just a minute. What Garrett does is he looks at that family and he projects it onto the annulus, and he counts the degree of that map, and that is a type 2 invariant. So it's very interesting. He also considered 6 distinct points on knots, and he called these satanic. Sense of humor here, I don't understand. And there are thelmic circles. So, can I do this in public? So he shows these kinds of things. This has degree 0. For various technical reasons, they don't always have to occur. I'll talk about this in a minute. Let me show you a movie. How do I make this big?
There's on the right. There's two arrows. Yeah.
Ah, there we go. So this red point will walk around the knot. That's the 1 dimensions. And then these circles each intersect the knot with this kind of ordering. So I will pause it at a nicer place. Let's try again. No. Where is If I go back a tiny bit. That one's quite good. Hang on, let me just keep playing. It's very interesting. Whoops. Same movie. So I don't know. I guess if we look at this one, and you go around and you compare. So I'm starting here and I'm walking around to here, but where do I go on the knot? Like I'm shooting, I'm going everywhere on the knot before I actually reach this point on the circle. So if you compare walking along the knot with walking along the circle, you'll see this pattern. But it requires some thought. So I'll just keep playing that again. It's very addictive. He has the code to produce these pictures in the back of his master's thesis. So let me...
What's the knot?
I don't know. I don't know. I haven't figured that out. It could be a trefoil, it could be a figure 8. I'm not sure.
You cannot change the...
No, I can't. So, okay, let me just go back to this. So, more results about using quadrisecants to approximate polygonal knots, which Professor Jin and Sojung have done work on, and we're going to hear a talk tomorrow. Yay! So I'm not going to say anything. Can wait to hear this. Very interesting. So this is the result I talked about. Oh yeah, so I thought I'd finish with some open questions. There's a lot. So Morton and so I think this is the big thing. Relate the number of different types of quadrisecants to other knot invariants. It would be nice if we could say, we have this knot and this polynomial. There are 10 flipped and 5 alternating or something. It'd be nice. Because the finite type invariant, the V2, is not that good. So Morton and Mon conjecture that you have, if the crossing number of your knot is n, then you have at least n choose 2 quadrisecants. Greg Kuperberg, what about wild knots? How many quadrisecants? How many alternating quadrisecants? Don't know. If a non-trivial link is disjoint from some topological plane, then it has 4 collinear points. So this is to do with the algebraic surfaces. Everyone can see that if you're a trefoil knot, I can't draw knots in public.
학계용 의지 연습 튼튼해요 국가학부 2012년 의지 연습이 8월 20일부터 23일까지 실시됩니다. 직원 여러분의 적극적인 참여가 평화롭고 안전한 미래를 맞추는
Is that it?
직원 여러분의 발전과 협조를 당부드립니다. 감사합니다.
Is that a fight?
Yeah. No.
No?
That's it.
We're okay?
The union announcement.
Okay. Okay. So Every trefoil knot, right, just has alternating. Where's the other one? Here. You can find a representative of the trefoil which just has alternating. So, and then other ones, the symmetric one, this I learnt from Professor Jin and his great pictures. This one has 2 flipped and 2 alternating. It's very interesting. So my question is, what about essential flipped and essential secants? Maybe all figure 8 knots have one of these. They'll have alternating, but maybe they'll have these. Maybe 5-2 have these. I don't know. What can we say? And the same question holds for these co-circular. Now Garrett, with 6 points, there are trefoil knots and 5-1 knots that do not have this kind of situation, do not have these circles. So maybe you can say something about knot type with more than 6 points. Like maybe you could say something. And then we'll learn about this conjecture during Sojung's talk, but a quadrisecant approximation is isotopic decay. Maybe it's true, maybe it's not. Maybe it's true with a minimal number of edges. You will say more. Maybe. Okay, so this is a very difficult problem. So I'll finish here. I've talked to John Sullivan and Cliff Taubes a lot about this work, and I want to again thank you for the invitation.
Are there any questions?